This whole time we've been finding things like acceleration and velocity. Now we're asking, why doesn't something move at all, like a house or a bridge or a hanging light? This is called equilibrium. And if an object isn't moving, then the net force and the net torque is zero. However, this doesn't mean that there's zero forces acting on an object. It just means that all the forces acting on the object cancel out and balance so that in total they add up to zero. So for equilibrium, there's two conditions. The first condition is that net forces must equal zero. So every horizontal force equals zero, every y force equals zero. And when you're dealing with 3D motion, every z force will equal zero as well. But we don't have to worry about that because we're dealing with 2D problems. So there's no net force sideways and there's no net force up or down. Zero acceleration in any direction. This either means that it's at rest or it's moving at a constant velocity that's not changing. Usually we're talking about something at rest. Before moving on to the second condition, I'll show you a quick conceptual example for the first one. Imagine a sign that's being hung like this. It's a very, very heavy sign, like 100 kilos. If it's staying still, the net forces must add up to zero. It means that the horizontal component of this chain must balance the horizontal component of this chain so that it doesn't wobble side to side. The upward pull in total must equal the weight of the sign, and that's what would hold it in equilibrium. What's the second condition for equilibrium? The second condition says that the net torque has to be zero as well, because even if the sum of all forces, so the net forces, equals zero, the object can still be rotating, because that doesn't mean torque is zero. Imagine an old shed, and this old shed has a door. You decide to try and open this door with your smart physics brain. You put a wooden plank, you wedge it underneath, and you put a brick right here. It's like a lever, and you use all your strength and you try to push down on the end of the wooden plank to open the garage door. However, the door doesn't budge. What do? There's two different ways that we could try and increase our power. We need more torque, which means that we need more leverage. So the first way, let me draw a better diagram really quickly. Okay, here's our diagram. This is the garage door from the side. This is our wooden plank, and this is the brick. If we need more leverage, the simplest way would be to extend our wooden plank. So find a longer plank. What this would do, well, because the lever arm is now longer, that means there is more torque. And if our new wooden plank is long enough and there's enough leverage, then the torque we provide should be enough to open this garage door by rotating this plank up. The other way we could do this is by not extending our wooden plank, but by moving the brick closer. So let's push it up here. Suddenly it's easier. Let's look at this mathematically. If this distance here is r, and this distance here is big R, force of the door is gravity, and the force of our push we'll label with Fp. When you move the brick closer toward the garage door, your big lever arm value increases a little bit. But here's why it actually helps so much. Torque has to be zero, correct? That means the torque from your push should equal the torque of the garage door. So, since torque is F times the lever arm distance, we can set up an equation. The force of the garage door, which is mg, multiplied by the lever arm here, should be equal to our torque, which is the force of the push times big R. This equation can be rewritten as R over R equals the force of push over the force of the door. If you're wondering why we can write it like this, is because if we cross multiply here, we get this equation again. And don't worry, this is not a skill that you need to know. I'm just trying to demonstrate why it affects the lever arm. The brick gets moved to the left, closer, which reduces our small lever arm and increases very slightly our big lever arm. Because this is a ratio, then it changes dramatically. That means because this gets smaller, then the force of our push would naturally get smaller as well to keep this equation balanced. So we push with less force, but we have more torque. That's the two conditions for equilibrium. But how about stability and balance? There's three types of equilibriums. I'll go through all of them one by one. The first one is called stable equilibrium. And this happens when an object is tilted, causing the center of gravity to move up. This means that the object wants to fall back to the original position. For example, if you have a pendulum, so this is a pendulum, and it gets pushed up. And right now the force is acting on it. You have the force of the string, you have tension and gravity. It balances out. It's at equilibrium, it's not moving. But when you give it a push and you tilt it, there's the force of the tension, force of gravity, and the center of gravity makes it want to go back to its original position. This is called stable equilibrium. The second type of equilibrium is unstable equilibrium. If you tilt this kind of object, the center of gravity moves down instead of up, which means that the object falls further away. For example, an inverted pendulum, like a screwdriver on a table, and it's balancing like this. This screwdriver, let's look at the forces. We have the normal force and we have gravity. And when you tilt it, so let's say you give it a little nudge, it ends up falling over like this. But have a look at the forces. The center of gravity is here. So gravity is pulling down like that. But the normal force is still here. So it falls further away from its original position. It's unstable equilibrium. The final is called neutral equilibrium, which means that when you tilt an object, the object stays in its new position perfectly fine. It doesn't fall back to its original one, and it doesn't fall further away. For example, you have a rolling ball on a flat surface. The center of gravity is here. If you push it this way, and it starts rolling like this, the center of gravity stays at the same height, and it stays in its new position. This is neutral equilibrium. So to sum it up, whether or not an object goes to its original position depends on the center of gravity when you tilt it. If the center of gravity goes up, it's stability. If it goes down, it's instability. In real world, humans often change their posture for stability, like when you're lifting heavy furniture. The center of gravity has to adjust. You have to change posture if you're lifting something heavy on your back. This makes studying 10 times easier. Go download the free cheat sheet in the description and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.